Okay, working with my logarithms again. We will eventually get to the calculus. We only got one non-calculus problem left. This is it. Expressed as a single logarithm. So I want to put these guys back together as a single logarithm. So it's going to be my properties of logarithms again, but going backwards, so to speak. That addition can be put back together in multiplication. Subtraction can be put back together as a fraction. But notice most of these things that kind of put things together, that combine my logarithms, they do not have coefficients in front of them. Addition can be combined back together in multiplication. Subtraction can be combined back together by making a fraction, but we don't have coefficients. Our rule that talks about coefficients is the power rule here, and a coefficient can go up and become an exponent. So looking here, what I have to do first is I have to start with the coefficients. So I'm going to start here on those guys, and I'm going to use the power rule. And so this will become natural log of x cubed plus natural log of y squared minus the natural log of y squared minus 1. Then these guys use the product rule, I should say power rule for logs, and product rule for logs. That addition can be put together by making a product. And then finally, use the quotient rule for logs. And we get the natural log of x cubed y squared over y squared minus 1. And there we've written it as a single logarithm. This does not simplify. Some people are going to be, some people are going to be, speak slower, Lori. Some people are going to be tempted to cancel the y squareds. They don't cancel. You don't get to cancel from a fraction unless you cancel from all terms in the fraction. And because you're not going to cancel anything from that 1, you're not going to cancel anything. Okay, so now it's time to do the calculus. And I want to find the derivative of the natural log. Now, you might think that the only tool we have in our chest here to do this would be the definition of the derivative, but we got some other things handy which will make us be able to do this without going all the way back to the definition of the derivative. So if y equals the natural log of x, or that's y equals log base e of x, then e to the y equals x. That's one of the primary things about logarithms, that you have that property that exponentials and logarithms kind of switch things around. So what we're going to do is we're going to use implicit differentiation on e to the y equals x and see what happens. So I differentiate everything, but every time I differentiate a y, I follow it by dy dx. So e repeats, derivative of the exponent, I just differentiate a y, dy dx. So there's repeats, derivative exponent, then implicit differentiation, derivative y x. And derivative of x is 1. So I have dy dx. Won't skip so many steps here. So I have e to the y dy dx equals 1. Or that's dy dx equals 1 over e to the y. But recall, y equals the natural log of x. That's what we have up here. Y equals the natural log of x. So I've got 1 over e to the natural log of x But e's and inverses are, e's and natural logs are inverses. They cancel, and I get 1 over x. And so what we just showed is, right, if we have y equal x, dy dx would be the logarithm. So what we just showed is that the derivative of the natural log of x is 1 over x. Now, I'm not going to ask you to reproduce this. Again, from a cultural standpoint, that sometimes we can get things at things kind of indirectly, that we went through the natural exponential function and implicit differentiation and got what the derivative is. Now, I did leave some things off. X is assumed to be positive because we are not doing logarithms of negatives. And so then we have it stated officially down here. The derivative of the natural log of x is 1 over x for x greater than 0. Now that's going to get a little bit boring. Derivative of natural log of x, 1 over x. So expanding that a little bit, more generally using a chain rule, the derivative of the natural log of u. And now as we start getting these derivative formulas and later on integration formulas, whenever you see u represents a function. It's not just a simple little plain variable. It represents a function. So the derivative of the natural log of u is 1 over u du dx from the chain rule. The natural log part gives us the 1 over, and then we go inside to that function u, the chain rule times through the inside function du dx for u greater than 0. If I don't know for sure that u is positive, we'll slap absolute value around it. Then the derivative of the natural log of the absolute value of u is 1 over the absolute value du dx. I'm not going to worry greatly about the absolute value. If you should have absolute value, you didn't. I might write it in there. I might not. The place where you'll have to worry is with the homework. That if the computer wants absolute value and you didn't put it in there, it will count it wrong. Now, a good trick or a good technique is to click on View an Example. Don't use View an Example. That's not going to help you learn things. But click on View an Example. Just get to the end, see how they answered. And if they answer with absolute value, you should answer for absolute value. Now, in words, to differentiate logs, natural logs, it's 1 over the argument times the derivative of the argument. And you should memorize that. And that just builds the chain rule right into it. So let's start differentiating. And we'll do this guy twice. Doing it just with my words. 1 over the argument, and then very, very specifically, showing way more detail than you have to do, derivative of the argument. So 1 over argument, ARG is argument. Derivative argument. And you certainly wouldn't have to show that first step. Then taking that derivative, multiply by the exponent, decrease the exponent by 1, and we are going to simplify this. And so that's 3t to the 1/2 over 2t to the 3/2 in a fraction. I subtract my exponents. So I'd have 3 over 2t to the 2/2. 3/2 minus 1/2, 2/2. Showing everything I could show. So 3 over 2t. Or simplify first. So there we simplified on the end, and it wasn't horrible. But notice if we simplified first, simplifying first, that exponent can come down in front and be a coefficient, and now it's just a coefficient. I do not need a product rule. Coefficients we just write down. Then very technically, 1 over the argument, derivative of the argument. And And obviously, you wouldn't have to write the times 1. That's just me being very specific. And I get 3 over 2t. And that was a little bit faster than the way we had done it before. Okay, next question. Product rule. I've got x times the natural log, so I have to use the product rule. So doing a product rule, plane first, derivative of the second, plus plane second, derivative of the first. Product rule. Plane first, derivative second, plane second, derivative first. And you certainly don't have to show that step. So I get to the second step, plane first, do nothing. I get to my logarithm. 1 over the argument, derivative of the argument. I'm up to the plus sign. Plane second, don't do anything. Derivative first, times 1. And then all we can really do to simplify that is say that's 2x over 2x plus 1 plus the natural log of the quantity, 2x plus 1. And nothing else simplifies. Those two x's don't cancel because you only cancel in a fraction if you cancel from all terms in a fraction. Okay, let's end this video.